So I'm talking about holographic complexity and some related ideas, but I wanted to start by saying that I've been able to work with a lot of smart people on various projects in this direction, and so I wanted to acknowledge all of their contributions as well. Um, Anybody who's seen me give a talk in, say, the last 5-10 years knows that I start with this slide here. About holographic entanglement entropy. And this is a very interesting idea that Tadashi introduced on the first day, and Veronica actually talked about it and new interpretations in terms of bit threads. But it's really been the engine that stimulated a lot of the it from Qubit activity and thoughts about bringing quantum information into holography and into quantum gravity. And it really, their beautiful formula here relating entanglement entropy in the boundary to the Bekenstein-Hawking formula in the bulk has really been teaching us new lessons both about quantum field theories and also about quantum gravity. And so I like to say that it's really produced a fruitful dialogue that's been going both ways in the ADS-CFT. And it really gave rise to, an idea that entanglement was a key element in the emergence of space-time geometry. However, a few years ago, our friend Lenny Susskind wrote a paper in which he said entanglement is not enough. But what he really meant to say was entanglement entropy is not enough. And in some sense, very much like the last talk, what he was saying is that entanglement entropy is just one measure or one diagnostic of entanglement in a quantum system, and there are many others. And we should pay attention to some of those others, as we saw in the last talk. In particular, the question he was interested in was what's going on inside a black hole, in particular deep inside, say, near the singularity. And well, there are some simple experiments that you can do that suggest that entanglement entropy is just not a diagnostic that's going to tell you about that region of the space-time. And so here's just to get us warmed up, or maybe to help us into this, here's an experiment that I think was originally proposed by Tom and Juan in one of their papers, where we're going to do an entanglement entropy calculation. But what I'm really indicating by this picture is that I'm choosing a region or a portion of one boundary. That's my A, or well, I guess my A is up here. But I'm also including as part of my A region there that I've called A prime. And I'm going to ask, what's the entanglement between these two regions and all of the other boundary degrees of freedom? And if I choose, or I line those up and make them large enough at t equals 0 there, what I find is that the entanglement surface, or the Ryu-Takiyanagi surface, actually stretches all the way across the Einstein-Rosen bridge. And so I get these blue lines here to evaluate the entanglement entropy in the boundary theory. And now what I can do is I can take my time slice on both sides and I can start to push it up or push it to the future, and then I'll get a picture like that. And what happens is that the surface now starts to probe this region inside the horizon near the bifurcation surface, and we can detect that space-time there takes this pink color rather than the green color on the exterior. But if we keep pushing the time slice up, what happens very, very quickly is that there's a phase transition in the extremal surface, and in fact, that what we get is that at a time of order, the thermal time, the entanglement entropy is just given by disconnected surfaces, which only probe the exterior regions on either side. And I can continue up and that entanglement entropy just doesn't change. And so it's been saturated on that time scale. And so I'm not, with these entanglement or Ryu-Takayanagi surfaces, able to detect what's going on deep inside the black hole, but maybe only very close to the bifurcation surface. And so one of the things Lenny reminded us, is that the entanglement entropy is something that probes only the eigenvalues of the density matrix, and that's what makes it an interesting measure of entanglement. But his suggestion was that we wanted more sensitive probes that were perhaps sensitive to more of the phase or more of the structure of the density matrix, perhaps, or I've said more metaphorically or poetically, sensitive to the phases. And his suggestion was that we should think about a new quantity, which we'll call holographic complexity. And every time you see the word holographic so-and-so, what we're doing is we're mashing together a great idea from some other field with holography in some interesting way. And since complexity is a new idea to many of us, I should introduce what am I really talking about. And complexity is really nothing more than what it sounds like. It's how hard is it to do something? How hard is it to organize an IT from Qubit workshop? How hard is it to get to Bariloche? But in our case, the physics question that we're going to ask and apply complexity to is, how difficult is it to prepare a particular state in our favorite quantum system? And the way we're going to do that is we're going to use a particular model for complexity known as the quantum circuit model. And so there are a number of elements. The first element is that we may want to build a number of different states, but we're always going to start with one particular simple reference state. And so if it was a system of spins, we might look at the reference state being the state with all spins down. And then we want to build a unitary transformation that takes us from this simple reference state to our favorite target state. But we're not going to just allow ourselves to write down that unitary operator, but rather we're going to have a collection of a simple set of unitaries that may act only on a few of the spins at a given time. And what we're going to do is we're going to build this big unitary out of this simple set of gates. And so here's a map or a circuit where we've put together, or I've put together various gates, and it's going to take us then from the simple reference state to some target state on the other side. And the idea then, an extra ingredient is that if I'm really using discrete gates like that, it may be very difficult to get to any particular target state. And so the computer scientists have taught us that we should actually introduce a tolerance. By some measure, we should decide that if we get close to the target state, then we should be satisfied and say that our unitary has succeeded. But the question about complexity is, what's the easiest or the simplest way? What is the minimum number of gates that I need to produce this transformation from the reference state to the target state? Or alternatively, what I'm trying to do is build or find the shortest circuit or the optimal circuit to produce this particular operation. Now, if you've been paying attention to something other than your email, like Dan there, a question that may arise is, I introduced a number of different elements, but it seems that there's a lot of ambiguity in what I mean, or what the rules are in defining the complexity here. And couldn't it be that the number that I'm going to get, the complexity, is going to define on all the choices I make, for example, in the choice of the reference state, or the choice of the gates that I use in building my unitary transformation? And the answer is yes. And so that's just a property that arises when we start to work with complexity, and it's something that we're going to have to get used to. It's something that arises at various points in the talk, But it's just a feature that when we're dealing with this particular approach or this particular quantity, there are these extra ambiguities. And so if I give you a set of rules and a family of target states, you may calculate a set of numbers for the complexities for each of those states. Someone else may choose another set of rules. They'll choose, or their favorite set of rules. They'll get another set of numbers. And something that we're going to have to learn is, are there robust questions? Is there what are the questions that are going to be interesting? What are the questions that are going to tell us about physics of these particular states? Or what information can we really extract from the complexity? Okay, well, Lenny did not just come up with this idea of coining a new name, but he also came up with a number or a pair of proposals with various collaborators on how we should evaluate the holographic complexity. And by construction, both of these definitions of holographic complexity probe the interior of the black hole to arbitrarily late times as I push my time slices up in this particular configuration. So the first of these goes by the name complexity equals volume. It's very similar to the idea of holographic entanglement entropy, or the construction looks very similar. What I'm doing in this particular case is I'm picking a time slice in my boundary theory. So in the black hole, I pick a time slice on the left and on the right. And then I look for, or I look at the codimension 1 surfaces that extend from into the interior from those boundary time slices. And I evaluate the volume of those codimension 1 surfaces, and I find the extremal surface, which in this case happens to be the maximal volume. And then I evaluate that quantity, and that dimensionless quantity gets called the complexity in this complexity equals volume prescription. And so that was something that Lenny first developed with Douglas Stanford, with a number of other collaborators, including Ying there, who's also reading her email. There's also the complexity equals action scheme. Well, in a number of transparent, in particular at the end, one of the questions I have is, what is holographic complexity? So I'm going to have to ask you at the end what that really means. Okay. In any event, in that case, what I can do is, for example, well, we've picked out some Cauchy surfaces between our favorite boundary time slices, and I can look at the domain of dependence or the causal development of that particular Cauchy surface. That defines a region in the bulk space-time, and I evaluate the gravitational action on that. I might be motivated to throw in a very particular normalization factor, and that gives me another quantity, another interesting bulk quantity, which we call the complexity in the complexity equals action prescription. So we have these two interesting prescriptions that now I've described the mechanics of how we evaluate them. What I didn't tell you is, why should I think this has anything to do with complexity of the boundary states? And I'm just briefly, I'm going to put up some indications that both of these may be related to complexity. I'm not going to go into the details here. One of them in particular, complexity equals volume, is closely related to some ideas in tensor networks. There are arguments that you can make that say that the complexity at late time should be growing in a way that's proportional to the mass, or rather in these conformal field theories, it's growing in a way that's proportional to the temperature times the entropy. And in fact, what I'm showing there is the result of a calculation that at least at high temperatures on the left-hand side, you get the complexity equals volume quantity growing in that particular way. And on the right-hand side, we also get a similar answer with a different prefactor, but it's again proportional to the mass. And there's also other observations made that when I perturb the system with shock waves, or I perturb the boundary theory with an operator, that there's a certain effect that's observed called the switchback effect, and it's observed in these holographic calculations in a way that one would expect. So that was very brief, but rather than dwelling on that, what I'd like to do is just show you some of the calculations that my friends and I did given these new gravitational quantities. And so the first was to answer a question that actually Ying and her collaborators posed, which is that when I think about the thermofield double, which is supposed to be dual to the black hole, what I have is 2 copies of the CFT, and I'm preparing those 2 copies of the CFT in a very particular state that's an entangled state between those 2 copies. But something else that I could have done, given 2 copies of the CFT, is just prepare each one in their vacuum state. And so a question that you might ask is how much extra complexity was required, how much longer a circuit was required to build the thermofield double versus just building the vacuum states. And so what we're doing is, what you would be doing is you'd evaluate the complexity for the thermofield double and then subtract off the complexity of 2 copies of the vacuum. In the holographic context, what you're going to do is evaluate, say, for the complexity equals action, I'm going to evaluate the action on this particular Wheeler-DeWitt patch in the black hole, and then I can do a similar calculation just for empty ADS space, pick a constant time slice. Here's a Wheeler-DeWitt patch that corresponds to that. I throw in a factor of 2 because there are 2 copies of the vacuum. And so you carry that calculation out, and what you find at the end of the day is a quantity that looks something like this. So there's some prefactor there that depends on the dimension of the boundary space-time. But then the interesting physical quantity that seems to appear in this complexity of formation is the entropy of the horizon, or in terms of the boundary theory, this is the entanglement entropy that you've introduced in the thermofield double state, the entanglement entropy between the 2 copies of the CFT. You may also have thought about putting the CFT on a sphere rather than a flat space-time, or you could put it on a hyperbolic space. And in that case, at finite temperature, there are various curvature corrections here that would be proportional to the inverse of the temperature times the radius of the curvature squared. But at high temperatures, those are small corrections to this leading contribution. That was complexity equals action. There's an analogous calculation. Oh, no, I wanted to say that that particular prefactor, although it looks intimidating, has a very simple linear form, or is very close to just a linear prefactor. I can do the same calculations or analogous calculations for complexity equals volume. You get a similar expression. There's an intimidating prefactor that actually is very simple, or it's almost just a constant. That multiplies, again, the entanglement entropy between the 2 copies. And then again, there are curvature corrections if you're at finite curvature or on some finite curvature space-time in the boundary theory. So this is an example then where we have 2 prescriptions, and we seem to be asking a question that gives us an answer that's telling us something about the physics of these particular state, or the thermofield double in particular. The details, though, of the answer are dependent on which prescription I use. Those 2 prefactors that depend on the boundary dimension aren't the same. And so you might think that this is evidence that both of these quantities, both of these prescriptions, are actually evaluating complexity in the holographic theory, although at the microscopic level, perhaps what we're seeing here is that the details of the rules of perhaps the gate set or the reference state are slightly different in these two different holographic prescriptions. It is equal to D for D equals 2, and what you notice is that prefactor vanishes. And so let's see if this got corrected. Yes, it did. Okay. So if you look at D equals 2, this prefactor, this entropy would actually grow with the temperature, but that first term actually vanishes, and so the first term, the first non-vanishing term, it turns out, is just proportional to the central charge of the boundary CFT. And again, the prefactors aren't the same, but you find similar results with either prescription for the holographic complexity. So that's one calculation. That's an example of the kind of calculation that you can do in this particular context and the comparisons that you can make. In another project, something that I did with Dean Carmi and Pratik Rath, is that, well, Lenny was focusing our attention on what's happening deep in the infrared or deep in the interior of the space-time, but you might also ask what's happening out near the boundary. Here we're evaluating quantities, we're integrating quantities all the way out to the asymptotic boundary, and so we expect to find UV divergences associated with both of these. In taking the difference in that last calculation, we cleverly canceled all of those divergent terms, and we were left with a finite answer. But let's just look at the, what kind of divergences we expect or we find in this particular context. We're going to regulate in the way that we've learned to regulate in the ADS-CFT, which is just not to integrate all the way to infinity. We introduce some cutoff surface that's related to, the position is related to a short distance cutoff in the boundary theory. And you can look at either of these calculations and look at the general behavior of the action or the volume as it approaches the asymptotic boundary in the ADS space. And what you find is, for complexity equals volume, something that looks like this. That's very comparable. This construction, I said, was very similar to the construction for holographic entanglement entropy, where you were hanging, in the latter case, a codimension 2 surface into the bulk. In the complexity calculation, you're hanging a codimension 1 surface into the bulk. But what you find is that the leading term is proportional to the volume measured in the boundary theory. That's the volume of my time slice divided by the cutoff to the appropriate power. There's some coefficient here that tells me about the number of degrees of freedom in the boundary theory, some central charge, and then there'll be some other prefactors here that depend on the dimension of the space-time. And then there'll be curvature corrections again. By that, what I mean is there are going to be integrals of various curvature quantities, say the scalar curvature of our time slice integrated over that time slice sigma, again divided by appropriate powers of the cutoff. And that's very much like what we saw in holographic entanglement entropy. Because the codimension is different, what came out here, or this first term, is what's known as the area law of the entanglement entropy, of course, but it had a very similar expression with the same central charge in Einstein gravity, some prefactor depending on the dimension. And then this is the relevant area where the extremal surface connects to the asymptotic boundary. And again, in these kinds of calculations, you also find curvature correction. So if I do, this was complexity equals volume. If I do complexity equals action, I get almost the same kind of structure. Well, in fact, I get, with different numbers, you get a similar series starting with the volume, and then there are curvature corrections. But then, in fact, there's a second series that has a very similar form, but there's this prefactor that sits in front that involves a logarithm of the cutoff. And that particular term, or that particular log, came from various boundary terms that had to appear in the action. And it's annoying for two reasons, and it's the other two factors that I didn't describe. I said there's the cutoff, delta, but that L is actually the ADS scale of the bulk theory, and that alpha is some normalization constant. I had this region of space-time. The boundary terms involve normals, but these are null normals because they're null surfaces. And so I have to come up with some prescription on how to normalize those normal vectors. And that's what the alpha reflects there. And that's annoying then for two reasons. One, this is supposed to be an answer of a question or a quantity in the boundary theory, and so it shouldn't know about the ADS scale. And the other reason it's annoying is it's got this alpha, and alpha is an arbitrary quantity. It's not fixed by the prescription or the complexity equals action or the definition that I gave you. I can use the fact that there are two problems there as a virtue to reduce it down to one problem, and that is I can write alpha as a ratio of the ADS scale over some other scale. This alpha is just a dimensionless quantity. In writing it in that way, at least I get rid of the ADS scale, but now I've got this new scale that I've called L here, and the question becomes, how am I supposed to choose my L? Well, it could be any scale, but we'd like it to be a scale that's relevant for every particular problem that we may want to study. It could be related to the size of the system. That's not entirely, or that's not satisfactory because then the complexity becomes super extensive. It could be that it's related to the UV cutoff. That has a problem in that now quantities that we thought were related or they were IR features of the complexity now depend on the UV cutoff. And that's simply because that same normalization constant that was producing this log out at infinity also appears in other terms because that normal has, well, that normal is the normal all the way around along those null boundaries. Alternatively, we could just say there's a new scale in the problem. It's the complexity scale, and it's not a scale that comes from the physics of the problem. And at the time that we first ran into this, I thought this was actually problematic and may indicate that there's a problem with complexity equals action, even though it just seems to be a technical detail. And I apologize for showing you that technical detail, but it will appear again towards the end of the talk. And so, well, those are a couple of examples of calculations one could do. You know, if you do these calculations, you run into lots and lots of questions. A real puzzle is, you know, you can generate lots of answers, but when we did entanglement entropy, you know, we had an intuition for how entanglement entropy behaves in various situations. And we could compare our holographic calculations with the expectations that we had in those contexts, say in two-dimensional CFTs. For complexity, we don't have any reference. We don't have an intuition or a very good intuition for how it should behave in a quantum field theory. And so that was a question that I turned to with some collaborators in the past year. What does it really mean to talk about complexity in a quantum field theory? So what we want to do is we want to take these rules here, but we want to apply them to a quantum field theory. Since I'm a big believer in taking small steps rather than giant leaps, we wanted to, or what we did is we started by, thinking about the simplest, or what I thought was the simplest possible quantum field theory, namely just a free scalar field in any number of space-time dimensions. And so it would have a Hamiltonian that looks something like this. What we saw in the holographic calculations is we should expect that the complexity is actually divergent. And so we should regulate this field theory. And so what we thought about is putting it on a lattice. Again, the lattice spacing now plays the role of delta, the short distance cutoff. But really what I've got now is I've reduced the problem down to evaluating complexity for an infinite family of coupled harmonic oscillators, which seems somewhat less intimidating than saying that I'm evaluating complexity for a quantum field theory. Okay, so we have our harmonic oscillators. What do we want? Well, the first thing we needed was a reference state. The reference state that I'm going to choose is a factorized Gaussian. It just says that each of the sites, each of the oscillators is in a Gaussian state, and they're all decoupled from one another. And so there's no entanglement at all in this reference state between the different lattice sites. I want a set of gates or unitaries from which I'm going to build my circuit. Well, the natural operators that I'm given in this problem, or that arise in this problem, are the momentum and positions of the oscillators. But it's easy to build unitaries. We just take exponentials of combinations of these. And in the problem that I'm going to study, the relevant gates take this particular form. You might recognize, if this was just some C number, you would recognize that as a translation operator that's shifting X. In this particular gate, what I've done is I've paired Pj with Xi, and so I'm shifting the Xj in my wave function by an Xi, and so I'm introducing entanglement between those two sites in the lattice. I've introduced an epsilon there in the exponential, though that's going to be a small parameter, and it's going to make sure that these gates, when I apply a single gate, it's only going to make a small change in the reference state. And so I'm going to have to introduce lots and lots of gates to produce a finite transformation. The other gate that I'm using here, I call the scaling gate, and I'm just shifting, if you like, X by itself, where I'm rescaling a given lattice site. So those are my gates. What kind of target state can we use? Well, there are various collaborations that I've been in. We actually started with Roe Jefferson, just studying the ground state of the system that I gave you on the previous transparency. Another obvious one is to think about the thermofield double, because that was the thing that was dual to the black hole in the holographic situation. And so that's something that I hope we're going to finish a paper on soon. A characteristic feature of both of those states is they're both Gaussian states, and that's what lets me get away with just using these particular simple gates here. So what am I supposed to do? I'm supposed to take my reference state. I've got a particular target state picked out, and then I'm just going to act with whatever, some particular set of gates, say Q11 to some number of times, then I'll act with this one some number of times, et cetera, et cetera. And the idea is I build a long string of these gates here that take my reference state, the factorized Gaussian, to my favorite target state. Then I count up all of the exponents here. That counts up the number of gates in that string. And that's what I'll call, not the complexity, but I'll call it the circuit depth. Because what I'm supposed to do is I'm not supposed to just find an arbitrary string like that, but I'm supposed to find the optimal circuit, or the shortest string of gates. So how are we going to do that? Well, there we're going to employ an approach put forward by Mike Nielsen and collaborators in the mid-2000s, and he was actually borrowing ideas from Hamiltonian control theory. But the idea there is, the first ingredient is, rather than thinking about those discrete strings of gates, I'm going to think about smooth functions. And so I'm going to replace my string by this quantity here. It's an exponential. The operators here are the operators that appeared in the exponentials that were my gates. And there's a string, or there's a path that runs over the parameter s from 0 to 1. These quantities here are just going to be like the exponents, but they're going to be quantities that tell me when along that path, I turn on a particular gate or turn it off. So that looked like an on-off function. S, again, that was a label that gave me the position along the string. The epsilon has disappeared in this notation, but you can think that the epsilon's been replaced by the ds, or the delta s, in the integral there. And there's a path ordering that just says that we're building up this circuit from the left to the right as it acts on the reference state. The other thing that Mike told us to do is not just think about the final or the total unitary, the entire quantity here, but to think about taking it from s equals 0 to some arbitrary position along the trajectory, or to think about how the unitary gets built up, and to think about trajectories then through the space of all unitaries. And so here the integral doesn't run from 0 to 1, but just from 0 to s. At s equals 0, I'm starting with the identity. At s equals 1, I'm going to have whatever the final unitary is that's going to produce the transformation that I want. And in that particular context, I can recognize these quantities here not as on-off functions, but as actually velocities along these trajectories in a very specific way that's given by that formula there. Now, then, what I seem to be thinking about is trajectories with velocities, and I want to minimize a cost function. And as physicists, we can think that, well, what I have is some particular action, and I'm thinking about a particle motion, and what I want to do is I want to minimize the action, or I want to find the extremal path. The natural cost function is one like this, where I take absolute values of the y's, the velocities, or the on-off functions, integrate them along the path. In that particular context, what Mike Nielsen argued is that what you're doing is you're studying geodesics in something known as Finsler geometry. But a simple thing to do is just to change that cost function to something like this, where it's the square root of the square of the velocities. That's something that we might recognize now as a geodesic in Riemannian geometry. You can also, I had delta ij there, but you can also favor different gates or give them different weights, introduce a gij or a more general metric. That's a simple extension. I'm not actually going to talk about that, or that's not going to rise in the talk later on. But I'm also going to think about more general cost functions that I'll call a kappa cost function, where I just take powers of the velocity to some exponent kappa and sum them up. For cap equals 1, I would have recovered the original cost function. For cap equals 2, that would be something that we're familiar with for a classical motion with the velocity squared. But in general, we might think about just arbitrary exponents there. And what we would be doing is just extremizing the equations of motion for this unusual classical action. So there are lots of calculations, there's lots of interesting geometry, and I'm not going to inflict any of that on you today. I'll just tell you about some of the results. So the first one was the ground state complexity. Remember, our target state was this factorized Gaussian. No, the reference state was factorized Gaussian. The target state is also a Gaussian, but it's most simply organized in terms of the normal modes. And so each normal mode is a Gaussian with a width that's given by the physical spectrum of the theory that's given here. If you go through all those calculations using this Riemannian geometry, what you find is the complexity is given by a simple expression like that. And if you stare at that for a while, what you'll realize is that I gave you the reference state in the position space, where it was this factorized Gaussian, but you can also sort of reorient yourself, and you can think about the reference state in the normal mode basis as well, and it remains a factorized Gaussian. And so what you're doing in this particular context is you're just taking each of the normal modes from a Gaussian with a fixed width where all the each normal mode has the same width, to the Gaussian where the width is fixed by the spectrum or the dispersion relation in our physical theory. And so that's why each one of these logs is just saying that I'm scaling up each of the normal modes. There's a square and a sum and a square root, but that's the answer. Yeah? The oscillators in this basis are implicitly coupled. The different sites are coupled because what I've done is a Fourier transform. So before I had xi's, those were positions in the lattice. I've done the Fourier transform, and so these x tildes are Fourier transforms of the xi's. So in the free field theory, the normal modes are not coupled, but implicitly there's some complicated coupling now for the position space representation. I mean, it would just involve putting the inverse transform into that exponential twice and transforming back. What can we say about that? Well, just like, well, in field theory, we expect that the answer is dominated by the UV modes, or well, in this particular case, it turns out that I was looking at a periodic lattice that had a distant or n lattice sites in each direction, each spatial direction. When the momentum's around n equals 2, or the frequencies are around 1 over the cutoff or 1 over the lattice spacing, those are the dominant, that gives you the dominant contribution here. And if I just substitute omega is 1 over delta into that expression, that of course simplifies the answer, and I get something that looks like this. It's n to that particular power, but I said that I was on an n by n by n lattice, so n to the d minus 1 is essentially the volume, and so what that's saying is that the complexity proportional to the volume over the cutoff to the appropriate power, but then there's this 1 over 2, or there's a square root. And so the leading contribution to our vacuum complexity goes like that square root of the volume. But that contrasts with what we had in holographic complexity, where we expected it to go, the complexity to go to proportional to the volume. And so we can think about where did that square root come from, and it really came from the choice of the cost function. I had this particular simple cost function because that gave me a problem that I was familiar with, this Riemannian geometry, but it's got this square root, and that square root is really this square root here. And that's why I wanted to think about more general cost functions, these kappa cost functions, where there's no square root on the sum. And if I make this choice here, oops, okay. If I make that choice there, I get essentially, well, I get this modification for the vacuum complexity. If I make this substitution here, now I get an answer that's proportional to the volume. And again, that's basically just I took away the square root that sat over that particular sum. I've also got this logarithm here, and the logarithm depends on that reference frequency that appeared in the reference state. And so I have to think about how do I choose this omega naught. And so I'm getting close to the end. You know, it's a scale. I have to come up with a choice. One choice would be that it's an IR scale, perhaps related to the volume, perhaps just some infrared scale in the problem. Then I would get my complexity to leading order looking like this, or it would look like the volume times a logarithm if I chose that kappa equals 1. And I chose that because that compared, or that was very similar to the answer that I was finding in complexity equals action. Another choice is I could choose that omega naught to be, you know, somewhere up at the cutoff scale. Then this logarithm would just, well, the cutoff would cancel and it would just turn into some number, and then the leading answer would just be proportional to the volume. As we saw both, there were terms like that in complexity equals action and in complexity equals volume. So, you know, there's this reference scale, and there are various choices you can make that may be satisfactory, unsatisfactory. But I put that green box up there to compare it to a green box that I showed you before. Remember, we ran into almost the same problem, and I told you, if in fact, an identical story about how there was an extra scale in the problem and there didn't seem to be a completely satisfactory answer. And whereas I thought it had been problematic, here I've done the simplest quantum field theory calculation, and I found exactly the same feature arose. And so rather than being a problem, it turns out that this is simply a feature. It's a new kind of issue or a new kind of property that arises in these complexity calculations. Very briefly, since I've run out of time, but I know I have a generous chair, we can ask about, we can think about the thermofield double, and in particular, we can evaluate complexity, the complexity of formation. In the limit where the mass is equal to 0, what we find is the complexity of formation up to some prefactor is again proportional to the entropy. And so this compares well with our holographic results, except for this special case d equals 2. We really find that in d equals 2, it seems that our quantum field theory answer is still proportional to the entropy, meaning that it still grows with the temperature, whereas remember in the holographic case, the leading term was just a constant. You can also, you don't have to focus on the massless case or the conformal case, and then there are curvature corrections to this particular answer. You can also think about the time dependence. In this particular case, well, the graph looks something like this. If you go through some calculations, here's an example for a three-dimensional boundary theory and various implicit choices. And what you see is that actually the complexity decays and then saturates on about the thermal scale at a value that's proportional to the entropy again. That contrasts with what we expected to see, or what you might have expected to see from holography, where again there's some kind of transient, but then there was this linear growth, and we might have expected to see saturation at some very high level at some very, very late time. But I think this is just showing you that, well, I was doing a free field calculation. This is a strongly coupled field theory, and so the comparison has to break down at some point. And so this is just an example that, you know, we're asking a question where the comparison can't be made. There are lots of questions that one might ask about complexity or to push this program forward. And I'll just end by saying that there's lots to explore. Thank you for your attention.
We have time for a few quick questions.
On your field theory results, I would like to know that, can you say anything about Lloyd bound being preserved or not?
Well, I didn't talk about the Lloyd bound, but in the so you're asking about the quantum field theory, but I want to answer about the holography, because in the holography, something I didn't show you is that in the thermofield double case, well, it's almost on that transparency. You wouldn't have known it, but in this transient here, you actually violate the Lloyd bound. But there have been even more dramatic violations shown in holographic complexity. There's, and I apologize to all the grad students who I'm not going to name, but Willie Fischler and some students in Texas showed that for the holographic dual of a non-commutative field theory, there was, the rate here was off by a factor like 5/4 times the Lloyd bound. And then more recently, Brian Swingle, and again, grad students in Maryland, in hyperscaling violation geometries showed they could get arbitrary violation, or what seemed to be arbitrary violation of the Lloyd bound. And so I mean, it was an interesting idea and motivation for complexity equals action, but I think that's one of the ideas that didn't really hold up in the end. So, well, yeah, I don't know. That's all I have to say.
I want to get a bit closer to holography. There's two things that I could imagine doing. One is turning on a coupling, so like studying lambda phi to the fourth theory.
Yeah.
And the other is going to large N, where you would maybe want to start with, I don't know, like the free ON model or something like that. Have you thought about trying to do that?
I thought you were going to say, and then I take an orbifold.
Yeah. People would have made fun of me if I said that, so.
Okay. I actually think that's an interesting idea. But,
it's the same thing. I mean, that's an ON orbifold in some sense.
Yeah.
You could do SN.
We have thought about introducing interactions, but only perturbatively. I haven't really, well, other than toying with it in conversations with various people about sort of these symmetric orbifolds, I haven't really done any calculations on that. But I encourage people to think about it. I really think it is an interesting possibility where you might be able to make progress.
Very well. So I don't see any further questions. Let's thank Rob again. And break for coffee.